Namaskar, welcome back. So, this was the last slide where we were talking about the safety measures one should take when before entering into the trench. Okay, and I was discussing about that this trench which we were doing in Punjab region, the foothill zones of Himalaya, and how difficult it was to find the helmets uh, for our protection. Finally, we ended up having 3 helmets gotten from the whole market, and that was again which have been used for riding the motorbikes. Now, after cleaning the trench, I will come to that slide also where how we clean and all that. It is always advised to map this type of exposed sections in the trenches uh, with greater details. Nowadays, we also do photography detailed and very close up photographs have been taken, and then you can mosaic it on your machines like PC. Okay, you can do on computer. So, and there are softwares which are also available, which helps you in cropping the grids in exactly the same size. Okay, so that can be done, and that should be done because you don't have any sort of a distortion. So why? Because you need to calculate or you need to measure first the slip during different events. If you are coming across uh, multiple events, evidence of multiple events in your trench, then those informations are required for calculating all geometric parameters. So further, as I told in the previous uh, lecture also, that we mostly use the backhoe, and this is again depending on that how big trench you are planning, that then you can accordingly choose the either the smaller machines or the bigger machines with the chains and all that. So that can, because this machine has an advantage to move horizontally in all directions. So that helps in putting up the excavated material on a farther side away from the trench walls. Okay. So as I told that this was the trench, which of course we did was very long, almost like 55 to 60-meter long trench, and almost like 5 meter deep. Okay. But unfortunately, we were not able to see a very clear cut deformation in this trench. Now, this we have done the trenches in the various different areas. Like this photograph is from Gujarat, Kutch region, where we did paleoseismic studies for on active faults. And this is a smaller trench. Okay, and if you closely observe the photograph here, there is a mountain front which is sitting on the background here, and the frontal part we don't see much of the topography. Only a very small scarp we can see here. Okay, otherwise the rest of the area is either eroded or modified. But we were able to find the fault somewhere here. Okay, I'll come to that because we have a couple of slides from this trench, which uh, talks about that how we did the retro deformation. Okay. Now, this is another picture of the trench where, again in Punjab, now with proper helmets and all that. But cleaning is very much important. Okay, so you may have to soil yourself cleaning the trench uh, properly, because you need to expose uh, each and every unit. Okay, that is important for in terms of the in mapping and also understanding the deformation uh, pattern as well as the events, number of events. Okay. So in this trench, if you quickly look, like try to understand, then you have a gravel unit which is bending here, and then it is following this line. Okay, and there is another one contact. So sharp contacts, if you just mark, then that can help you in understanding what is happening. Okay, so this is again another one, and this portion has been overlaid. So this is your soil unit in between, and this is another contact. So what we call the bonding surfaces. Okay, so this is a quick interpretation you can do, that you see a definitely and very prominent deformation in this area. Okay, and as I told that one has to be careful and need to clean. So if you see this trench, this was another trench adjacent to the previous one on the same fault, and you can see the topography here. This is the fault topography, we can say, and the fault, as we were talking about in the beginning, maybe in the previous one of the previous lectures, that fault will sit at the toe of the scarp. Okay, and this is exactly what you see here. Okay, so this is the toe of the scarp. Fault trace is over here, and fault plane, it goes right up to this one. Okay, so this is a very clear cut and very beautiful example which also justify what we were talking about. Okay, so mapping is important, and then what we have done is we have put 1 by 1 meter by 1 meter of grid on this, and that is been sketched. Okay, so all information has been taken up on a tracing sheet or maybe a graph sheet you can use. Okay, where you can have the same scale, smaller scale on the representative scale, you can use that, and then mapping has been done, and each and every contact has been marked. Okay, we have different tools which can be used, and we are comfortable using couple of tools which were, I would say, that invented or available in Japan. Okay, which the farmers uses. Okay, and this is what we call, this is for cleaning, and this is known as a nijirigama. Okay, so this nijirigama is good for cleaning the trenches and all that, but other than that you can have a lot of other things, because you need to have brush to clean the trench. Okay, and of course the previous slide we were using what a commonly used shovel and all that in our Indian side. Okay, we use that what we call fawada and all that. Okay, so these are some tools which are required for cleaning the contacts, cleaning the material which is falling on the wall. So that has to be brushed and cleaned. Okay, there is another way of doing or cleaning this, is that you spray water. Japanese style is that they keep cleaning the trench using a very like not strong but very soft spray they will put of water, and they keep cleaning the trench. Okay, that is another way out. Sometime it is advantage, you have an advantage, because each material, because there will be different layers or the sedimentary units exposed in the trench, and will have different absorption nature. So that process will allow you to demarcate the units very clearly. So this is an advantage of. And another part is that if you come across gravels, and that is fluvial deposits, again the finer ones are fluvial also. So that part also you will be able to clean it properly. Okay, so in this trench particularly, we uh, use partly water and all that, but we were not having enough water supply available here. And the reasons why we did not use water is that the walls were collapsing. So you can see that we were not able to go up to this portion. This portion started collapsing. Okay, so we left that part anyway. But we were fortunate enough, as I told, that we were able to expose uh, the most deformed portion. Okay, in the trench. Okay, so if you can see here, there is a gravel which comes here, and then it goes like this. Okay, so this is the amount of displacement you have. Okay, so you can calculate the slip right into this. This is what we call the net slip you will be able to get. And what I am doing here is that I am taking the readings of the fault dip. Okay, how much is the angle of the fall dip and all this. So there are minor information, or you can say the minute informations you will have to uh, look at. Okay, for uh, for having the detailed information from the trench. Okay, then as I told that you need to sketch this. So we are exactly, so here the student, she is giving the measurements with respect to your grids, individual respective grids, and that same is been transferred on this graph sheet. Then, as I told that this the Japanese people are very fond of spraying the water on walls. Okay, so this is what we did in Kutch with a Japanese team. We opened up a trench and we kept on cleaning this area. So we were having some jet pump with us, and we cleaned the trench maybe number of times, and then removed. Again, you can see that we are using this Nijerigama over here, okay, to clean the trench walls. Okay, then final outcome has to be something like this. Okay, so this is on the graph sheet. As I told that we we put the grid one by one depending on what how deep trench, or how what is the height of your trench. Depending on that you can do, but usually we are comfortable putting 1 meter by 1 meter of grid. Okay, and then you have to even number this grids. Okay, so if you see here, then this is showing if you start from here, probably this is 2 and this is 1, and the numbering which has been given is 1e, 2 it goes up to 8e. Now E is representing east wall. Okay, east facing wall, or east wall you can say. Okay, similarly you have to also look for the west wall. Okay, if suppose your trench is oriented north south, then you will have east and west wall which are exposed. So that is the coding which has been done, and coding for each vertical grid line has to be done. And at the same time, what I was mentioning, that a, this type of sketches, it includes everything, including the fault plane, and then also what we call this fabric. So the fabric of the sediments, okay, and mostly gravel, if you see, then you will be able to judge even that what is the pattern of deformation here. So after thorough cleaning, you will have to mark the discontinuities, okay, or you can say the tectonic unconformity, and you need to be careful what we have learned in the previous lectures, that whether this type of contacts are depositional contacts, erosional contacts, or they are just what we are looking for, that is your tectonic contacts. Okay, so the result of these contacts are because of the tectonic deformation. So that part has to be very carefully studied in field. And as I told that we also use photo mosaicing, and this is the trench which we open up in Pinjore, across Pinjore Garden Fault, of like almost 25 kilometers. This place is located from Chandigarh. And in this, again, at that time, we were not having the digital format. Okay, so these are the normal paper print photographs developed in the lab, and then they are mosaicked. Okay, but here the mosaicing will not be so perfect. Then also it was quite good enough to have the overall uh, picture of our trench. Okay, and again you can use the softwares to trace each and every grain in the trench. Okay, right now I'm not having that slide, but maybe next time I'll show you that that how detailed we have done the like mapping of this fabric. Okay, I would say. And we also sometimes talk this we use the word shear fabrics. So in this, if you broadly, as I was talking about that broadly see that what are the prominent changes in the sedimentary units, okay, in terms of the color, in terms of the grain size, okay, and then how they are been distributed across the exposed section, you can easily make out here, okay. So if this is like what we have marked as an A as a gravel, a comparative gravel is also seen here, B, that unit is also here, okay, and then C here, okay. And then you have, if you look at the contact here, this is what we can easily mark, okay. Now after getting this, after I have put these lines, okay, and that what need to be done, okay. Again, you can clearly make out that this is an fold, okay, propagating fold along this line, okay. Okay. So this is your fault plane along which the movement is taking place. So if I try to show you here, then that is something which is going on like this, okay. So this side is your, what we call is the foot wall, and this one is your hanging wall. We'll talk about this as I have been mentioning number of times. We'll very quickly, maybe in coming few lectures, we'll go into the detail of what is the hanging wall and foot wall and all that, okay. So the sketch, final sketch, which was been prepared from the photo mosaic as shown above, the sketch, you can see that how what the amount of details we have put here, okay. And this helped us, if you compare this portion, okay, you just see this portion here, this helped us in even understanding that the gravels or the gravel layer is also folded, okay. Of course, it will get folded, but the shear fabric what we see here, okay, is very clear. So this type of, and then again, because if you try to look at this portion, this one, okay, sorry, this portion, it is bit difficult to put this contact here, okay, which has been put over here, sorry, like this, okay, this is the contact like this, okay. So this contact was difficult to put, but the fabric which we studied and which we were able to extract helped us in clearly demarcating these two units, okay. So this suggests that this portion of the gravel is deformed, whereas this one is undeformed. Hence, this has been marked as C, same unit. Of course, there is a deformation here within that, but this is the capping unit. Now, coming to the, after you identify these contacts or the bonding surfaces and make sure that they are tectonic or non-tectonic. Now, in this itself, of course, this deformation is related or this contact is related to the secondary deformation which took place, okay, or you can say the secondary feature. But this one, this contact is nothing to do with the deformation, okay. So this is your depositional contact. Now, after identifying and fixing your boundaries, what one can do is, let's see here, okay. Now, this was the trench where I was showing in the previous slide, where the Japanese guy is spraying the trench wall and that. So this is from Lodi, from Kutch, which was been dug across the Kutch mainland fault, or you can say another young fault which has been developed in that region, okay. And what I was emphasizing, that you need to identify each and every contact very precisely, and you need to measure the slip, and that slip, net slip, will help you because how you are going to calculate the net slip is very simple. Okay. So, if you have for example, the two layers here, okay, and they are displaced, okay, along the fault here. Now, if they are displaced like this, okay, for example, you are having this unit, like let us say this is A and this is B here, then A, and then you have B unit here, and then it goes somewhere like this. Okay, this is your A, and this one is your B. Okay. So, if you have to talk about the net slip, then this will be your net slip. Okay. The amount over here, the displacement, will be your net slip, and that what exactly we have done here. Okay. So, we have measured the net slip between two units, and that is one is between B and C, and then C and D. Okay. So, what we got and how we were able to justify that there were more than two events which resulted into this deformation, or there were two events on this fault. Okay. Or but probably there were more than two, because we see the zone of deformation here also. That was difficult for us to make the contact, but of course, you can see the contact between E and D. This is E and this unit is D. Okay. You can see the contact over here, that it goes like this. Okay. So, the contact is here like this, and then it is sitting somewhere here. So, this is the net slip of unit E. Okay. And whereas this one, this contact here, if you see, then it goes like this. Okay. So, this is the contact of your or net displacement of D, whereas this one is your net displacement of C. So, what we can immediately infer is that the D is having larger displacement. Okay. And similar to that, even E is more or less similar. Okay. So, D and E are showing comparatively larger displacement when we see the unit, this unit. Okay. So, that what we measured here, that the unit D was showing around 73 centimeters, and this was showing around 33 centimeters. Okay. Now, let us see what we have done. So, we just played with this, and what we usually do sort of in jigsaw puzzle. Okay. We tried that. Okay. So, east wall view of the trench excavated across active fault scarp near Lodai village, okay, across the Kashmir fault. Okay. So, what we did was that we cropped this portion of the trench, and then we played with it. Okay. So, to resolve two events, because we immediately looking at the amount of displacement, it was quite like appealing that probably there are two events, and this D unit has moved twice as compared to the B unit or the C unit. Okay. So, that has to be resolved. Okay. So, then we started doing that. Okay. So, this is, as I told, that it was showing 33 centimeters, whereas this one was showing 73 centimeters. Okay. So, the displacement along, and this was along F3 fault. Okay. This is F3 fault. If you see, this is along this one. Okay. So, this is your F3 fault. So, we took this because this was giving us the best indication of the difference in the slip. Okay. So, this we did, and then to resolve this, so we particularly used unit C, and then that provided excellent example. Okay. So, let us see what we did with this. Okay. So, we sort of cut and displaced this along this line. Okay. So, latest event we can say, where we are trying to match the boundaries of C. Okay. So, we displaced that and we matched that, okay. And that gave us the that it is 33 centimeters which has been pulled, okay, back, because we measured that 33 centimeters and we pulled that much back, okay. But still, so this is 33 centimeter, but still 40 centimeters has been left out because the total displacement of unit D was 73 centimeters. So, 40 centimeter is still left out. So, this 40 centimeter, the next event we removed and we matched with the upper bounding surface of D. So, that gave us the total displacement. This is 40 and this is 33, and this total becomes your cumulative displacement, okay, during two events, that is your 73 centimeter during event 1 and event 2. So, with this note I will stop here and we will see if we have more on this topic, or else we will start a new topic today. Not today, but in the next class. Okay. Till then, thank you so much. Namaskar.